Hi everyone, my name is Milad and today I'll be doing system design video. I hope that you enjoy it, and if you do, please do take a moment to subscribe, like, and leave a comment. With that said, let's dive right into it. Today I'll be designing a distributed caching service, and here are the goals I'm aiming for. Data retrieval and storage, TTL management, cache invalidation, strong consistency, data partitioning and distribution, and finally replication for high availability. Cache as a service is very simple in terms of functionality. We focus on 4 primary functions: set, get, update, delete. If we look at the API, pretty simple. We have API set. The body will contain key and value, and a TTL, which is optional. We will have an API get key. We will have API update with key value TTL. And then we will have an API endpoint to delete key. Here we will have a post, get, put, and delete. Because one of our requirements isn't data persistence, I will not be entertaining conventional databases. This, on a very high level, is all we need to get started. Now let's jump into our system. We're going to start really simple, and I will evolve this service to ensure we meet all our requirements. We start off with a very basic service. We call it cache. And then this service will allow us to perform the 4 functionalities we talked about. Now, to communicate with clients, we want to either allow direct access or indirect access. Conventionally speaking, and for best practices, we never wanted direct access to such a service, especially if we have external users. So we'll utilize an API gateway. This will allow us to capitalize on rate limiting, firewall policies, and a variety of other options that we wouldn't really be able to do without adding complexity to the caching service. Successful system design relies on the simplicity of your components and extensive monitoring. So on a very basic level, this is what we have. Now, when we talk about high availability, we always want monitoring. So we will have a logging service, which will log everything to ensure that we can respond and react to events that happen within our system. You can use Grafana, and a variety of other tools that are available, Datadog and a few other ones. See what works right for you. All right, so let's talk about the hardware that this service will run on. So cache will be RAM heavy, and that also gives us low latency, but we want different layers of speed, so we will also commission servers that will capitalize on SSD, and to improve performance, we will RAID those SSDs into RAID 1. Now, how do we use the cache? We can rely on programming that, but there are a lot of tools out there that allow us to immediately start using RAM in a very efficient way. So our caching service will utilize either LevelDB or RocksDB. And they have different use cases. Because of the simplicity of our system, we'll just utilize LevelDB. LevelDB is a local database that allows us to capitalize on the RAM availability and save our values to the RAM and retrieve them with ease. And because it's a key value style database, it basically fulfills the requirement we want while satisfying our latency requirements. Okay, so that, again, on a very basic level, is how our system works. A request comes in, the cache service determines what action to take, utilizes LevelDB to write to the cache, and either retrieve, update, or delete that value. Now, we want to also take care of our TTL. One of our requirements is TTL Management. And to do that, we will run an event called TTL job. And basically what this will do is run every X minutes. You can determine what is most appropriate for your system. It will iterate through the values in the cache, check the TTL, and for any TTL that has expired, remove that value. Okay, this takes care of our data retrieval and storage, TTL management, and cache invalidation. Next, we want to talk about strong consistency and data partitioning and distribution, replication for high availability. All right, so as we mentioned, this is a distributed system. That means there are multiple copies of this very service in multiple regions. And they will need to be able to communicate, synchronize, and work together to ensure they deliver a consistent experience for our clients. To do this, we have to be able to allow those systems to communicate with one another. To do this, we need a really fast connection that will also optimize sending and retrieving data. To do this, we will utilize RPC, which stands for Remote Procedural Call. It is a service that was developed by Google. It allows us to optimize communication with different servers and allow for quick response time. It works on top of HTTP2. It optimizes data sending and retrieval through serialization. And the protocol it uses is called protobuf, which stands for protocol buffer. It takes data, quickly converts it to binary, sends that across the network, and on the other end, it is quickly deserialized and utilized. All right, so here we got a system that allows us to now communicate with multiple different services to communicate events and changes that occur. While this allows communication, the challenge is consistency. So now we have to make sure our system is consistent. And to do that, we have to utilize another technology. There are a couple of options here, Paxis and Raft. Paxis is a complicated algorithm developed and studied for many years. And Raft is a more recent, simple algorithm that allows us to ensure consensus amongst many different servers. So we now introduce the Raft protocol into our system. Raft works through an election style approach where different clusters will elect a leader, and that leader will then determine what the other nodes should do to remain consistent. All right. So now what's happening here is a request comes in. If the current server is not the leader of that cluster, the request is sent to the leader via RPC. The Raft protocol will then determine how to keep all the other nodes synchronized, and once the agreement is made, the signal is sent back to all the other nodes to update accordingly. This will take care of our data consistency. And now we want to talk about high availability and data partitioning and distribution. When we're talking about data partitioning and distribution, there is nothing native that we can use with the technology that we are currently using. So instead, what we have to do is create that functionality ourselves. So what we have to do is create many instances of this particular server. So what happens is we have multiple nodes that represent this setup here. And then what we need is a load balancer. That will distribute the request accordingly. And to do that, we will use consistent hashing. To allow our system to scale up and down based on demand, what we will do is build our system on top of a Kubernetes infrastructure. This allows us to configure the system to scale based either on CPU usage, RAM usage, and other configurations. So what happens now is that we create different namespaces, and each namespace will be associated to a specific hash range. Hash range 1 and hash range 2. We can grow these indefinitely depending on our needs. And when a request comes in based on the hash, it will determine what server to send that request to. Now here we've got local partitioning and distribution. What we need now is the ability to replicate this in multiple regions. And to do that, we will have multi-zone deployment. And when you have multi-zone deployment, you need multiple load balancers. When a request comes in, we will handle it at the DNS level with a global load balancer, and then send that off to our regional load balancer, which will then direct that request to the most appropriate data center to handle the request. Now, there are multiple ways of distributing the requests. The algorithms you use and the conditions and requirements you will have will depend on your system's needs. This will allow us to have data distribution, replication for high availability. It's worth noting that with consistent hashing, you also get replication, because different servers will maintain data for more than just one hash range. There will be crossovers to ensure that if one server goes down, there are others that can come in and pick up the request and handle them as necessary. All right, guys, let's review. Data retrieval and storage, we satisfy that with our cache service. TTL management, we satisfy with our TTL job. Cache invalidation, handled with the TTL job and the cache service. Our data partitioning and distribution, none of them have native partitioning, so we will use consistent hashing to distribute loads and data to specific servers to process, store, and make available. Replication for high availability is both local and regional, and this satisfies what we are trying to do here. All right, guys, this was my attempt at designing a distributed caching service. Please take a moment and leave a comment. I would love to hear what you guys think about what I did right and what I did wrong. I'm looking to improve. Until next time, thank you. Please don't forget to like, subscribe, and definitely leave a message. Goodbye.